I'm Anil Kumar. Welcome to my series on exponential functions. We have 4 multiple choice questions here based on applications of exponential growth. The calculator is allowed, so these questions should be solved using calculator. We'll also see how to use logarithms to do the calculations when required. You can make a note of these 4 questions. You can see first 2. Here are question number 3 and 4. Once you've tried them, look into the solutions provided. Here is how we will actually solve them. Question number 1. The population of bacteria can multiply 10 times in 20 hours. If this exponential growth is maintained, then when will the population be double of what it was after 20 hours? Right. So generally when we are talking about exponential functions, the equation is kind of a, b, we can write rate of growth, and that is the time, right? So that is the exponential function, which normally we'll be considering to solve most of our questions. So once again, the population of bacteria can multiply 10 times. So this is the multiplication factor 10 times in 20 hours. Now, how could you rewrite your equation to incorporate this particular thing, which is 10 times in 20 hours? So we could write like this. This population at any point, I'm just using B, you could use population P, is initial population. The multiplication factor is 10, so we can write 10 here in 20 hours, so we can write T over 20. Now that is a neat way of writing your equation whenever you are given something like this. You are given a multiplication factor, right? Use this information to write an equation. That helps, right? Now, if this exponential growth is maintained, then when will the population be double of what it was after 20 hours? So we are comparing two populations. The one after 20 hours and then thereafter when it gets doubled, right? So we don't know when will it get doubled, right? So let us say now we have that population after 20 hours will be what? So let me say, let's say B, population after 20 hours will be, when T is 20, correct? So it will be A times 10 to the power of 20 over 20, which is basically 10 times A, right? This is what is said already. Now, when will it be double to this? That is what we want to know, right? So, time is not known. So, double of this means 2 times 10 times A is what we need. That is double of this. And this equation remains same. 10 to the power of T over 20. So when will it be twice this, right? Since double of population at 20 is 2 times 10A. Is that clear to you? So we get a straight equation here which can be solved. Only unknown here is T. Perfect. So you can simplify this. And you can take log on both the sides. So when you take log on both sides, so we get log of 20 equals to T over 20 log of 10. Right? The log of 10 is 1. So we can just multiply this by 20. And we get our answer, which is T is equal to 20 times log of 20, right? Since we know log of 10 is basically 1, correct? So let's use our calculator to find this answer. So it is 20 times log of 20. which is equal to 26 point something. So 26 hours is the right answer. Do you get the idea of it, right? So that is how we could easily solve this. Now looking back into our solution, see how simple it becomes. Double of what it was after 20 hours. We got the answer 20 log 20, right? From this situation, divide by log 10, which was 1. So it is 26 hours. Now let's take the second question. The population of bacteria can multiply 10 times in 20 hours. After a day, how many times as great is the population as it was after 20 hours? Right. So after a day means T is 24. Let me use P for population this time. So again, from our situation, we can say population at any time T is initial population, as you normally write, 10 times in 20 hours. So 10 times in T over 20. That is how we got our equation, correct? So that's another way of writing in function notation the equation. So population of bacteria can multiply 10 times in 20 hours. Multiplication factor is 10. After a day, how many times as great is the population as it was after 20 hours? So population after 20 hours will be initial population into 10 over 20 over 20. So this population, of course, as expected, is 10 times the initial population, correct? Okay. Now let's find the population after a day. After a day means 24 hours. How many times as great? So population after 24 hours will be initial population into 10 to the power of 24 by 20, correct? So that will be right. Now we need to just compare the two rates. You could simplify this, but now since we need to just compare, then we can write the ratio population after 24 hours to population after 20 hours. These are the two things, right? After a day, how many times as great is the population as it was after 20 hours? So we are comparing these two. So you can write this as P0, 10 to the power of 24 over 20. And here it becomes P0, 10 to the power of 1, which is 10, correct? So that is their ratio. So this is what we need to calculate. Initial populations cancel, right? So we have here 10 to the power of 24 over 20, which is, we can use a calculator to calculate, right? So we have 10 to the power of 24 divided by 20. That is in the numerator. And then we are going to divide this by 10. Simple as that. It becomes 1.58. So that is the ratio. So the closest in our solution is 1.5 times. So we'll take this as the right option. Is that clear to you? Perfect. Now let's move on and take question number 3. The population of bacteria is growing exponentially. The number of bacteria after 15 hours is 50% higher than what they were after 3 hours. In what hour will the population be 3 times of what it was after 1 hour? Now that is extremely tricky and very different from what we had in the first two cases, right? Now it really says that the population of bacteria is growing exponentially. So we do have exponential growth. Now the number of bacteria after 15 hours are 50% higher than what they were after 3 hours. So that means, let's try to understand this situation. So what we're trying to say here is that from 3 hours to 15 hours, which is 12 hours period, right? During this 12 hours, the number of bacteria after 15 hours 50% higher 50% higher means what factor? So it increased from, let us say, 100 to 150. That is 50% higher, right? Do you see that? Right? So that means what is the ratio? So the ratio basically is 150 divided by 100 or 1.5. So we got that multiplication factor. So this information actually gives you the multiplication factor. Do you see that? So we have a multiplication factor which we say is the rate of growth is 1.5 times. So we'll write 1.5 here. Do you understand how we get that R value from the given condition? Right? And this happened in what duration? In 12 hours. So this multiplication factor of 1.5 is in 12 hours. So we'll write here T over 12. Now you get an idea how easily we can actually convert this information into an equation. Got it? Now that is kind of critical to understand. So with earlier simpler example, we did get the same thing, right? 10 times in the given period of 20 hours. Do you remember that? So it's almost the same thing, but we have used percent in this case, made it slightly more complicated. But I hope now you can make the connection. Now let's see what we need to find. In what hour will the population be 3 times of what it was after 1 hour? So P1 will be when? When I write T as 1 over 12. Now what we want? We want this ratio PT over P1, which is 1.5 to the power of T over 12 over P times. We call this initial, normally we write P0, right? No harm in writing this. Over 1.5 to the power of 1 over 12. Clear? Now say, in what hour will the population be 3 times? I want this ratio to be 3. So do you see how easily we could get our equation? And clearly, this initial population cancels. So in most of such questions which we have seen, initial population doesn't make a difference, right? So we need to now solve this particular equation. We can solve it using logarithms, correct? So we can write, taking cross multiply this. So we have 1.5 to the power of T over 12 equals to 3 times 1.5 to the power of 1 over 12, correct? We can take log now both sides. So let me move on this side, take logarithms. And then we'll go to this place, correct? So in that case, we get T over 12 equals to log of 3 times 1.5 to the power of 1 over 12 divided by log of 1.5. Clear? Okay. So T will be 12 times this. So let's calculate. So the initial value is log of 3 times 1.5 to the power of 1 divided by 12. Right, so that's the numerator. We are dividing this by log of 1.5. So we get that as 2.79. So we'll multiply by 12, 2.79 times 12 equals to 33.5. Do you see that? So we get 33.5, and the closest answer is C, which is 34 hours. And that is how we are going to solve it. So I hope it is absolutely clear. So have a good look at it. Also understand how we got this equation, the factor of 1.5 and this exponent T over 12, right? Question number 4. The population of bacteria is growing exponentially. The number of bacteria after 2 hours is 250 and their count is 350 after 4 hours. How many bacteria will be in this culture after 8 hours? So this is relatively simple. It's exponential growth. So we write population at any time is equals to initial population into rate of growth over t, right? So what we are given here is that the number of bacteria after 2 hours is 250. So P of 2 is given to us as 250, right? So we say 250 is equals to initial value r to the power of 2. And the count is 350 after 4 hours. So 350 is the count after 4 hours. We have two equations. With these two equations, we can always find the value of R and P, right? So if I divide equation 2 by equation 1, in that case we get 350 over 250 equals to P0, this cancel, R to the power of 4 over R square, which is basically 4 minus 2 R square. And so R is square root of 350 over 250. Correct? So we can actually find this answer. So we have square root of 350 divided by 250, and that is approximately equal to 1.1832. So we'll take 4 decimal places for accuracy, right? And since that is the case, we can use this equation 3 and equation 1 to find initial population, right? So from here, we know initial population is 250 divided by R square, right, which is 1.1832 square. So we'll divide 250 by 1.1832 square, and we get this as 178.57. So we have to round this to a whole number. So we'll take this as 179. Right. So we'll take that as our initial population. Sometimes you may have to find the initial population, rate of growth, and all those things also, and therefore this part I've done like this. Correct? Now we need to find how many bacteria will be in this culture after 8 hours. So that means P of 8 will be P of 0 R to the power of 8. Now we know P of 0 is 179, and R is known to us 1.1832 to the power of 8, correct? So we get 179 within brackets 1.1832 to the power of 8. Right, so that's the answer, which is equal to 687.57. So the closest is 680. So we can round this to 687, right? So that is how we can actually do the calculations and find our answer. You could actually also use the strategy which we used earlier, and that is to get a formula with the given information that in 2 hours, how many times it gets multiplied, right? So we could also use this, that the population is basically initial population, and in 2 hours. So bacteria after 2 hours is 250 and their count is 350 after 4 hours, right? So within this duration of 2 hours, right, by how many times it has changed. So it has changed 350 over 250 times. So that is the ratio, right? And we can write this T over 2. So that equation can be formed from the given information. You get the idea? So the ratio of the numbers is the rate, and the duration is 2 hours, so T over 2. Correct? Now, when you want to find how many bacteria will be in this culture at T, we are actually finding, we need to find P0 also. Otherwise, we'll have to compare with these ratios, correct? So we could compare and find. But if it was how many times the bacteria will be after 8 hours, we'll use this equation. So if the question is, let me see, question 4b. Question 4b now is how many times will the bacteria number be after 8 hours as compared to that after 6 hours. So if I change the condition like this, comparing with two different times, this becomes a better way of solving, right? Well, you could do both ways also. You can find both the numbers separately and then also get the same answer. So here is where we're going to end. But I hope you understand in this exercise, we kind of compared the two values for an exponential growth. And we formed an equation in that situation and solved. Calculator was utilized to find the values, and we also understood how logarithms could be used to solve such questions. I hope that makes sense. Feel free to write your comment, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.